So here YL is the parallel combination of RLC. So I'm going to expand the parameters above the frequency omega naught using Taylor series. So I'm going to go a little bit mathematical. So I'm going to expand the equation for YAE in terms of with respect to omega naught, which is going to be my resonant frequency. So YAE equal to GIE plus J omega naught into CIE plus J into omega minus omega naught into CIE dash, plus you will also have terms like J into omega minus omega naught the whole square into CIE double dash. We have like Taylor series, you know, it's an infinite series, it goes on, but I am considering the first DC term plus our fundamental frequency two terms J omega naught CIE plus J into omega minus omega naught CIE dash. So I am considering the first term and neglecting the remaining terms. This is I am considering from the Taylor series expansion of Y parameter. So similarly, I wrote the expression for input admittance YAE. Similarly, I also write the expression for output admittance also Y naught E. Same way, Y naught E is equal to G naught E plus J omega naught C OE plus J omega minus omega naught into C dash OE. So this is going to be the expression for the Taylor series for the output admittance. So I'll same way it will have infinite number of terms, but I am stopping with the three term DC term plus the first fundamental component term and the second fundamental component, which is going to be deviating from the frequency omega. It is omega minus omega naught into COE dash, and dash means it is differentiation. I'm going to differentiate the YAE term with respect to d omega. That is how mathematically the Taylor series, their terms will be differentiation as you progress. So the first term is DC, second term will be your actual capacitance. CI. See, these are not capacitance values. They are the coefficients of your. They are coefficients of your Taylor series. Don't confuse them with the capacitance values. Okay, the CIE, C dash IE, C naught E, and C dash OE are all the coefficients of the Taylor series. So now I can, from the figure, from the simplified figure, I am going to write what is IA. So IA is equal to YRE into V out. So see here, IA is equal to YRE into V out. See, this current IA is going to flow through here. So this current and this source value are same. So IA is equal to YRE into V out. That is our first equation. So next to find out V out. What is V out? In this equation, you have one current source and two admittance are in parallel. So V out will be equal to the total current source into opposite admittance divided by opposite admittance plus that admittance into that YL value. Correct? So see the output side, I need to find out V out, and V out is measured across YL, and in the output side I have current source and two admittance in parallel. So see here, minus YFE V in divided by Y naught E plus YL. This is going to be the expression for V out. So minus YFE V in is the current source into divided by Y naught E plus YL. So you know when in parallel voltages are going to be same, and I can add these two admittance so that it's going to be Y naught E plus YL. The total current is going to be YF. The voltage will be equal to total current by admittance. So YF V out will be equal to YFE V in divided by Y naught